Hi there, we are Team 53 working on reinforcement learning for robotic arms. Quick introduction, we are working for packaging systems using the Aloha Trossin stationary setup, training a pair of robotic arms in order to complete unstructured tasks. The problem that we are trying to address is working through refining our own progressive learning algorithm and being able to get adequate data that can be passed on to the company's other robots so that they can be properly trained in whatever task the company sees fit for them at that time. Another problem is as the workplace is ever adapting and robots are expected to be able to adapt along with them. We want to work with a product that does not need objects to be placed in the same spot every time in order to work, but rather can adapt to their surroundings. The scope of our work is we are using reinforcement learning to teach our robotic set of arms how to complete different unstructured tasks, whether this is organizing, collecting, or simply moving around different objects to where they need to be. Our job is to make sure that the robots are able to interact with these items without them being placed in the same spot every time. How we are doing this is working solely off a laptop running both the Linux environment and ROS. We are running trial runs through the Aloha stationary setup, which are then transferred over and conducted in thousands of simulations, piecing each of these together so that the robots can learn the patterns and what it means to complete the task thoroughly. Working for the state-of-the-art, the FNOC robots, the ones you see in large auto manufacturers, are big, bulky, and while they can move objects around and be helpful in the workforce, they cannot be adjustable for their layouts. They are programmed to do one task over and over again, and we're looking to create something much smaller, much more streamlined, that is able to work alongside people, not just have one task. Also, we are working with the current reinforcement learning. This is a topic that is ever improving and changing drastically with how AI and other artificial intelligences are manifesting themselves in the world. And alongside that, we are working with packaging robots who follow many of the same patterns as the FNOC robots, and we want to be able to work with much smaller items and items that are changing in sizes, making sure that whatever we are programming and training the robots to do can be adapted to different scenarios. Our system solution, here's a photo of our Aloha stationary setup. As you can see in the red, these are the leader arms, the arms that are controlled by us or whoever the pilot is. And these each supplementally control a follow arm and the gripper attached to it. Along inside this setup, there is a set of cameras that allow the full data collection of the visuals, allowing to properly capture the position of both the arms and any objects that are within the area, so that when you are in control, the camera can see exactly what you see as the person, allowing the computer to properly diagnose that as you would with your own two eyes. Here is a quick video demo of us piloting. Here's the script.
Oh no.
Would you like the video?
I'm videoing.
Okay. I don't know. They've been bouncing. Maybe I need to.
Oh, you're so close though.
I know. When I came up at like 12:30. Maybe higher. We'll pull it back. And then when
Oh my God!
As you can see, this is just some of the simple tasks while we were starting to learn and get comfortable with the Aloha stationary setup. We wanted to make sure that we were able to properly use the grippers and arms in a way that would be far more complicated than simply grabbing, picking up, and moving. But we wanted to instead be able to do very precise tasks if required. Some of our results. Currently, we have the robot completed about 200 plus runs in order to properly train the robot for our desired task. To the right, you can see that in the top right with the many files, which include not just the video recording, but also the position, speed, and the movement code that was encoded off of the pilot controlled run. And on the bottom, we are currently running each of those through 2000 sims, piecing together all that data from each recorded run. As you can see, if you zoom in, it does require about 156 hours for this task. That was an 8-second task completed over about the 202 times, showing that with this small task and a small sample, it takes about 160 hours of computer processing. This is something that we're hoping to streamline with a greater computer, but in the meantime, it reflects on how much processing power is truly required to complete and properly train these robots. Here are references.